When you look up at the sky, you're seeing the history and the future of the universe. Our entire existence is tied to one star, the Sun, in a tiny corner of one galaxy. But how did that star come to be? How does it work? And what will happen to it when its life is over? We're going to explore the Sun's life story, from its beginning to its end, and the incredible physics that power it. Our entire story starts about 13.8 billion years ago with the Big Bang. This wasn't an explosion in space. It was the beginning of space and time itself. In the very first moments, the universe was incredibly hot and dense. As it expanded and cooled, the first and simplest elements formed, almost entirely hydrogen and a little bit of helium. Think of it as the universe's starting ingredients. These two elements are the raw fuel for everything that comes next. How can we be so sure about the Big Bang? We have two huge clues. The first is redshift. When we look at distant galaxies, we see that the light from them is stretched out, kind of like how the sound of an ambulance siren stretches and gets lower as it drives away from you. This tells us those galaxies are moving away from us, meaning the whole universe is expanding. The second clue is the cosmic microwave background. This is a faint, leftover glow of radiation, like a cosmic echo from the Big Bang, and we can detect it everywhere we look. So the early universe was full of hydrogen. What happened next? Stars happened. A star is basically a giant, self-sustaining bonfire in space. But instead of wood, it burns elements. And instead of being held in a fire pit, it's held together by its own massive gravity. A star is a constant battle between gravity trying to crush it and the energy from its core trying to blow it apart. As we'll see, that energy comes from nuclear fusion. Stars are born in giant, cold, dark clouds of gas and dust called nebulae. You can think of a nebula as a star nursery. Over millions of years, gravity starts to win. It pulls little clumps of this material together, like a snowball rolling downhill, getting bigger and bigger. As the clump, now called a protostar, gets more massive, the pressure and temperature at its center skyrocket. When it finally gets to about 10 million degrees Celsius, something incredible happens. Nuclear fusion ignites and the star switches on. Our Sun is one of these stars. It was born from a nebula about 4.6 billion years ago. It's not a particularly special star. It's not huge, it's not tiny. It's a main sequence star, which is the name we give to stable, adult stars. It's made almost entirely of that original hydrogen and helium from the Big Bang. Its massive gravity is what holds our entire solar system in orbit, from Mercury all the way out to the farthest comets. If you could slice the Sun in half, you'd see it's built in layers, like an onion. In the very center is the core. This is the Sun's engine. It's only 25% of the Sun's size, but contains half its mass. It is incredibly dense. Outside that is the radiative zone, where energy bounces around for thousands of years. Then comes the convective zone, where hot gas bubbles up to the surface, cools, and sinks like a giant, boiling pot of water. The surface we see is called the photosphere. This brings us to the most important part of our standard. How does the Sun's core actually work? It is a nuclear furnace. The temperature and pressure are so intense, 15 million degrees Celsius and 250 billion times Earth's air pressure, that atoms can't exist whole. It's a plasma of nuclei and electrons. In this extreme environment, nuclear fusion occurs. This is the process of fusing, or smashing, light atoms together to create heavier ones. Here's the real magic, and it comes from Einstein's famous equation, E equals mc squared. When the Sun fuses 4 hydrogen atoms into 1 helium atom, a strange thing happens. The 1 helium atom weighs just a tiny bit less than the 4 original hydrogens. That lost mass isn't really lost. It is converted directly into a massive burst of energy. The c squared in the equation is the speed of light squared. a colossal number. So even a tiny bit of mass m creates an enormous amount of energy, E. This fusion process in the Sun is called the proton-proton chain. It's a three-step recipe. First, two protons, which are just hydrogen nuclei, smash together. One of them changes into a neutron, and they form heavy hydrogen. Second, that heavy hydrogen smashes into another proton, forming helium-3. Finally, two of these helium-3 atoms smash together, break apart, and form one stable helium-4 atom. The reaction releases energy, plus two protons that fly off to start the whole process over again. The energy from this fusion process is born in the core as a gamma ray, a very high-energy form of light. But it doesn't fly straight out. The Sun is so dense that this photon of light will slam into an atom, get absorbed, and be re-emitted over and over. It takes what's called a drunkard's walk, bouncing around the radiative zone for, on average, 100,000 years. By the time it finally reaches the surface, it has lost energy and become the visible light and heat that travels 8 minutes through space to reach us. So if the Sun is constantly burning fuel, how long will it last? We can create a model for this. It's like looking at a car. If you know how much gas is in the tank, the Sun's total mass, and how fast the engine burns that gas, its luminosity, you can calculate how long it will run. Based on these models, we know the Sun has a total lifespan of about 10 billion years. Since it's already 4.6 billion years old, it's in its middle age, about halfway through its life. The Sun is currently in its main sequence stage. This is the long, stable, boring adulthood of a star. It's defined by one thing. It is steadily fusing hydrogen into helium in its core. The outward pressure from this fusion perfectly balances the inward crush of gravity. Our Sun will stay in this stable phase, not changing much, for another 5 billion years or so. We are lucky to live during this stable, quiet period. But in about 5 billion years, the party ends. The Sun will run out of hydrogen fuel in its core. When that happens, fusion stops and gravity wins. The core will collapse and heat up, becoming so hot that it ignites the shell of hydrogen around the core. This new, intense energy will cause the Sun's outer layers to expand massively. It will become a red giant, swelling up and likely vaporizing Mercury, Venus, and possibly even Earth. During the red giant phase, the core gets so hot that it will briefly start a new fusion process, fusing helium into carbon. But eventually, that fuel runs out too. At this point, the star becomes unstable. It will start to puff off its outer layers, releasing these massive, beautiful clouds of gas and dust into space. This expanding cloud, illuminated by the hot core, is called a planetary nebula. The name is confusing. It has nothing to do with planets. It's just the star's final breath. And what's left behind, after all the outer layers have drifted away? The dead, exposed core. We call this a white dwarf. It's the ember of the star. It's about the size of the Earth, but has the mass of the Sun, so it's one of the densest objects in the universe. It's no longer performing fusion. It's just a dead star, glowing white hot from all its leftover heat. It will spend the next trillions of years slowly fading to black. Now, this white dwarf ending is the fate for stars like our Sun. But what about stars that are way, way bigger? High-mass stars live fast and die young. They are so massive that their cores can fuse heavier and heavier elements, helium to carbon, then neon, oxygen, all the way up to iron. But iron is a dead end. When the core turns to iron, fusion stops cold. Gravity wins instantly and catastrophically. The star collapses and then explodes in a supernova, an event so bright it can outshine an entire galaxy. This explosion is what creates and scatters all the heavy elements, like gold, oxygen, and calcium, that make up planets and even us. You might be wondering, how do we know all this? We've only been studying stars for a few hundred years. We use two main tools. First is spectroscopy. When starlight passes through a prism, it splits into a rainbow with black lines on it. These lines are like a unique fingerprint or barcode for each element. We can look at a star's light and know exactly what it's made of. Second, we are cosmic zookeepers. We can't watch one star live its whole life, but we can look at millions of stars at different stages, babies and nebulae, adults in the main sequence, and corpses as white dwarfs, and piece the whole story together. All this energy released by the sun is the single most important factor for life on Earth. It's not just that it keeps us warm. That sunlight is the direct power source for photosynthesis. Every plant, every algae is a small solar panel, capturing that fusion-powered energy and storing it as sugar. When you eat a salad, or a cow eats grass and you eat the cow, you are consuming energy that was born in the core of the sun. That same solar energy evaporates water, driving our entire water cycle and creating all of our weather. Let's bring it all together. The sun is a main sequence star, halfway through its 10 billion year life. It is a massive nuclear reactor, powered by nuclear fusion, which smashes hydrogen into helium in its core. This process obeys Einstein's E=mc², converting a tiny amount of mass into a massive amount of energy. That energy, released as radiation, travels to Earth and powers every aspect of our lives. By studying other stars, we can confidently model the sun's future, from its red giant phase to its final quiet end as a white dwarf.